Good morning. My name is Matteo Repetto, and I served as technical coordinator of the GARD project. In this presentation, I'm going to give a brief overview of the main concepts behind this project and a quick demonstration of the final GARD platform. The GARD project started in May 2019, ran for 3 years, and hence ended recently. It involved 15 partners from 8 different EU countries. The GARD project was born to address the technical gap between information and communication technologies and cybersecurity paradigms. Advances in virtualization and software-defined systems has driven the ICT industry towards massive usage of cloud computing, including fog and edge models, network virtualization, Internet of Things, and their combination to build cyber-physical systems. Despite of this groundbreaking evolution, cybersecurity paradigms have not evolved at the same pace. As a matter of fact, the security perimeter is still the prevailing model, but it cannot effectively tackle security aspects of cyber-physical systems and systems of systems, like integrity, trustworthiness, and data sovereignty in an effective way. As a typical example of the reference scenario, let's consider a smart mobility application for citizens. This is representative of one of the project use cases and concerns the collection of information from IoT devices to provide smart services to citizens and operators of public services. This kind of service is a typical example of cyber-physical system encompassing multiple domains. As a matter of fact, there are several digital resources that are usually provided by different providers. IoT devices installed on buses are the main sources of data. The application could also be extended with information coming from other appliances, like smart lampposts, parking meters, etc. Data is typically collected through a LoRaWAN network, which pairs it to remote servers. A 5G slice or other kind of metropolitan backbone is used to provide the necessary connectivity to LoRaWAN gateways around the city. One or more cloud infrastructures are used for running the LoRaWAN network server, data processing backends, and visualization frontends. Finally, the cloud application itself represents the last link in the chain. For instance, it may be a fleet management application. Management interfaces are available that allow a service provider to quickly configure and interconnect these resources in a business chain. Some examples include fireware and daemon. However, the deployment of security agents is not possible, and service providers must typically build on security capabilities provided by resources owners. Cloud providers often offer security functions like firewalling, antivirus, intrusion detection systems. Unfortunately, common and homogeneous interfaces currently lack that are suitable to automatically compose such functions, so to create detection and analytics services for systems of systems. This demands for cloud access security brokers to enforce consistent security policies across multiple clouds. The problem of cloud access security brokers is that they don't stop the proliferation of heterogeneous interfaces and capabilities, but only hide their presence to organizations. Of course, this means they must be continuously updated to follow the evolution of cloud services and do not scale well with a large number of different domains and infrastructures. GARD pursued a novel approach where security capabilities are exposed by digital resources in terms of conventional monitoring and enforcement agents. While security entails a very broad scope, in GARD we focused on the implementation of detection and analytics processes only. The GARD platform is a sort of middleware that mediates between security functions implemented in digital services and detection or analytics algorithms running in the platform itself. After considering existing standards like Oasis OpenC2 and IETF interface to network security functions, we came to the conclusion that none of them fit dynamic and evolving systems. Therefore, we developed our own smart data model, which is able to capture the context in which each digital resource is running. This gives indication of the current hardware or virtualization platform, software, vendor, and version, as well as security capabilities available. There are two main innovative workflows brought by the GAR platform. The first one is discovery of service topology, which leverages the GAR smart data model to recursively find all elements involved in a business relationship, starting from an entry point that represents the root of the chain. The result of a discovery process is a service chain which nodes are digital resources composed to create the overall business service. One or more security agents may be present in each of these environments. The links represent logical relationships between them. For instance, an application hosted in a cloud infrastructure, a client-server relationship between applications, a LoRa network, and so on. These relationships are created based on the information exposed by the smart data model. They can be automatically derived from management interfaces used to compose services, hence the configuration burden for resource providers would be limited. The examples shown in this slide are concrete examples of service chains discovered in the GARD use cases.
In the GARD dashboard, service chains are visualized as graph topology. The discovery of a new chain is started from the Discovery Service Chain button. The discovery only needs the URL of the root service in the chain, including port number and the need to use the HTTPS protocol. Once the discovery is started, it takes a few minutes to complete, depending on the chain size. By clicking on each component, it is possible to show its main characteristics. At the end, the operator can adjust the visualization according to his preferences.
The second main innovation is represented by the abstraction of security agent. The GARD Smart Data Model implements an interface to security functions that allows to discover the functional model of an agent and get access to its available instances. Both models and instances are dynamically loaded in corresponding catalogs hosted by the platform and made available to security operators to create security analytics pipelines. GARD builds on and extends the abstraction layer originally proposed by Astrid for cloud applications. Security analytics pipelines are the implementation of detection and analytics services at runtime. The whole service chain is abstracted by its logical topology, which includes both description of the execution environments and security capabilities like monitoring and enforcement. Data collection, delivery, storage, and visualization are implemented inside the GARD platform based on Elastic Stack technologies. Runtime management concerns the selection of proper agent instances and the necessary configuration to feed the desired detection algorithm or analytics engine. The necessary configuration is largely automated by a smart engine, the security controller, which also takes decisions based on reaction policies associated to each security analytic pipeline. Typical reaction may include the automatic configuration of firewall rules or other forms of enforcement policies, which are configured through the same GARD abstraction and smart data model interface. Of course, the framework also provides token-based authentication and authorization mechanisms to restrict access to internal resources to authorized security providers only, which act on behalf of resource owners. The distinction between security and service providers is necessary to avoid conflicts in service management and security operations. We'll now see a quick example on the chain previously discovered. Let's assume an application deployed in a multi-cloud environment. We have local network scanners in each infrastructure, but they are not effective against denial of service attacks that saturate the internet pipe. We therefore make use of the scrubbing center model to implement detection and reaction to those attacks. We therefore access the security analytics pipeline section of the dashboard and create a new pipeline. The definition includes a mnemonical name for the operator. Then we have to select a proper agent instance. In this case, we use the VDPI monitoring tool developed by the project and select the only instance available in the infrastructure identified as scrubbing center. We also set proper parameters for the detector, which depend on the specific model made available from the resource provider. Afterwards, we select the detection algorithm, which in this case is a machine learning flow classifier developed by the project. We set a reaction policy, which triggers a firewall rule that drops all packets coming from the source identified by our detector. Our firewall implementation is the PGA filter developed by the project, which leverages eBPF technology. The next step consists in starting the pipeline. After successful notification, for the sake of this demo, we start a GoldenEye attack towards the main application protected by the scrubbing center. We can use the cloud dashboard of the infrastructure that hosts the application to see the current volume of traffic. After starting the attack, the volume of traffic suddenly increases with respect to normal activity. In the guard dashboard, we see that shortly an alert is generated with the source of the attack. This alert triggers the reaction policy and the configuration of the PGA firewall. Back to the cloud dashboard, we see that after a while the volume of traffic decreases. Overall, the application remains under attack for a few minutes. This interval is due to the time needed to collect flow information and to avoid false positives. Although the project successfully demonstrated the feasibility of the original concept, it is still a work in progress and several features must be improved before commercialization. The GAR Smart Data Model must be standardized in order to foster wider adoption by resource providers. Preliminary steps in this direction were already undertaken, and the parallel option is to propose extensions to OpenC2 to broaden the set of potential adopters. A broader ecosystem of security agents, detection algorithms, and analytics engines must be provided. This is indeed rather simple and limited to management aspects, since GARD already uses common protocols for data handling. The current implementation is quite limited in terms of automatic configuration of security analytics pipelines. Extensions to data enrichment and transformation are anyway necessary. This is quite straightforward from the technical perspective, but also requires some additional abstraction to properly manage the necessary transformation along the pipeline. The scope of security policies must be further extended to take full advantage of this automation mechanism. Specific aspects include configuration updates in case of topology changes, support for additional enforcement mechanisms, automatic derivation and sharing of CTI. For more information, please contact the project and technical coordinators or our communication manager. GARD is also present on the web and main social media. Thank you for your attention.